Hi, my name is Yurii, and today I will present you the work called Contextual Embeddings for Ukrainian, a large language model approach to Word Sense Disambiguation. This paper is done by Yurii Laba, today's speaker, Volodymyr Mudryi, Oles Dobosevych, Dmytro Chaplynskyi, and Mariana Romanyshyn. Word Sense Disambiguation, or WSD task, involves identifying a correct meaning of a word with multiple senses in a given context. Let us see the following example. We have the sentence «Сторож бряснув ключами, смикаючи важкий здоровий замок», which can be translated to English as «The watchman rattled his keys, prying open a heavy, big lock». The word «zamok» in Ukrainian has multiple meanings, including a door-locking device, a clasp in a knuckle, a device to fire a shot, a fortified building of a feudal or a prison building. So the WSD task consists of identifying the correct meaning of the word zamok based on the context. Typically, researchers rely on supervised datasets while solving and evaluating the WSD task. Such datasets consist of pairs of sentences and sense for a particular lemma, along with binary labels indicating the usage of a lemma in that specific context. Here you can see the sample from such a dataset. Unfortunately, no such dataset is available for Ukrainian language. We decided to build such a dataset for evaluation based on the SUM dictionary. It also helped us to dive deeper into the nature of polysemy and homonymy in Ukrainian. Let us see what the SUM dataset looks like and what information could be extracted. Here on the slide we can see the lemma "luty". In English, this lemma could be translated as angry. Our lemma has a couple of quite similar possible meanings, such lemmas are called polysemy lemmas. On the next slide, we can see the various examples of sentences with lemma "luty". It's also important to mention that the examples in SUM dictionary were taken from a broad selection of resources, including fiction, Ukrainian translation of the Bible, folklore, scientific and popular scientific works, the language of mass media, etc. But the word "luty" is also a homonym. That means that there are two or more words "luty" in dictionary with totally different meanings and origins. In our study, we've decided to concentrate on homonyms as it's easier to distinguish between their meanings. To build a good quality dataset based on the SUM dictionary, we've also applied some cleaning techniques. Among them, we may highlight the following. Remove lemmas with length or fewer than 3 characters. Remove lemmas with missing senses or examples. Remove lemmas that belongs to functional parts of speech. Remove lemmas which lexical meaning reference for another lemma. So, after all preparations, we obtained the dataset in the following format. Here we can see that the first two examples are polysemy, meaning mother. The next example, starting from the third one, are also polysemy. On the next slide, we can see the example of the homonymy version of the dataset. Here we combined all the possible lexical meanings of a particular polysemy lemma. This means our dataset now consists only of samples with totally different meanings, homonyms. Let us now discuss the prediction logic of our solution and the most important part it consists of. As you may see on the screen, at the input we have the particular lemma and the sentence with this lemma being used. As the next step for this lemma, we have two groups of possible lexical meanings. Each group consists of all combined possible lexical meanings of the lemma. The next step is to calculate the embeddings of all meanings and embeddings of the particular lemma in the example that was provided as input, using large language model, which we will discuss further. Then we calculate the cosine similarity between the embedding of each meaning and lemma embedding. Then we choose the meaning with maximum cosine similarity as predicted meaning of the input lemma. To measure the performance, we use a simple accuracy metric. In practice, it looks the following way. We have the lemma, a group of all lexical meanings of this lemma, and sentences where this lemma was used. We also have a predicted context by the flow that we discussed earlier. And as a result, the label that indicates whether the prediction matches the actual meaning or not. Let us briefly discuss how we calculate embeddings to represent words and sentences numerically. At the input, we have a tokenized sentence or lemma. This data goes as an input to the transformer model that produces the embedding of the following shape: number of tokens times number of layers times embedding size. Then we apply the pooling operation and receive the final numerical representation. The embedding pooling is quite an important process while calculating the final numerical representation of sentences. Various pooling strategies could be applied, resulting in better or worse results. We've experimented with various multilingual transformers and pooling strategies in our study. In particular, we've experimented with mean pooling that compute the average of the embeddings for each token from the last hidden state of the model, max pooling that extract the maximum value of the embeddings for each token from the last hidden state of the model, min-max pooling that calculate the average and maximum values of the embeddings for each token from the last hidden state of the model, and concatenate the resultant vector. Concatenate pooling that concatenates the embedding from the last 4 hidden states, last 4 or 2 sum pooling that sums the embeddings from the last 4 or 2 hidden states. Based on our experiment, the mean pooling alongside one of the sentence transformer models, paraphrase multilingual MP-NET base version 2, showed the best results. So we decided to continue fine-tuning that model. After choosing the baseline model, we started to think of the proper loss function to increase the model performance. We came up with the idea to use the triplet loss. Triplet loss is a loss function that minimizes the distance between the anchor and positive sample while maximizing the distance between the anchor and the negative samples. But the question was raised, where to get the needed dataset. We decided to build a dataset in a triplet format, which consists of an anchor, a positive, and a negative pair. We define the positive example as a sentence that uses a lemma in the same context as the anchor sentence, while the negative example uses a lemma in a different context. We used an unsupervised methodology to obtain a dataset. Specifically, we used UberText, which contains text from Ukrainian periodicals to collect a large number of Ukrainian language sentences. You can see the examples on the screen. Then we removed sentences from our homonym evaluation dataset that did not contain any lemmas. We represented such a dataset in numerical format using the transformer model. Utilizing the cosine similarity function, we were able to build triplets. The idea is that we've calculated the cosine similarity between pre-calculated embeddings of all sentences that contain the particular lemma. For each sentence, we found another sentence with the biggest and the smallest distance and consider them as a positive and negative examples. Our hypothesis that the positive pair are the sentence with a lemma used in the same context and the negative pair lemma used in the other context. After mining process, we obtained a several version of fine-tuning dataset. The dataset consists of approximately 190,000 samples with 9.8% of the relevant samples. The dataset consists of approximately 1.2 million samples with 20.8% of the relevant samples. The dataset consists of approximately 1.1 samples with applying some similarity threshold metric filter with 13.1% of the relevant samples. Our PMMB version 2 model that was fine-tuned on the 1.2 million samples with filtering achieved an accuracy rate of 77.9%. Here you can see the accuracy per part of speech. For nouns, verbs, and adjectives, the model fine-tuned on the 1.2 million samples without filtering showed the best results, while the best accuracy for adverbs was received on the filtered dataset. Also, bigger dataset leads to the better results. We also test if our model did not predict just the most common sense. So we calculated the accuracy for the PMMB version 2 per the frequency of sense usage. You can see this information on the slide. The PMMB version 2 model fine-tuned on the filtered dataset shows better performance for top 3 frequencies of the sense usage. So our final model works even better for less common senses. To sum up, we built an evaluation dataset for the VSD task for Ukrainian language using the SUM dictionary. We proposed a novel approach for solving the VSD task in under-resourced languages such as Ukrainian. Our approach achieved 77.9% accuracy on the homonym dataset. Thank you for your attention.